if you take in power electronics or any modeling class, you're going to have some series resistance and some inductance because it's actually a wire. So these are the series resistance and series inductance. Can't be completely left out. So this is if it's just a hunk of like a PN junction sitting there, but it also works as a photovoltaic source, right? So you have to model the sunlight coming in to the panel, and we did that using this source called a photocurrent. Okay, so this is kind of the model I'm working from, and one thing that's not captured in this aspect is reverse voltage, which is kind of the key to hot spotting and understanding what can happen when the cell gets compromised. But if you reverse, so you can just think of it as a diode. If you reverse, they have that breakdown voltage on a diode, right? If you go above that reverse breakdown voltage, it will act like a zener and go through. So that's the last part that we'll talk about. So with this in mind, let's go back kind of to what the standard is. The industry standard is a single diode model. And we have this diode again from the PN junction. And we have the series resistance here and the parallel resistance here and the photocurrent. But we're missing the capacitance and the other inductance. So this is a really simple way to do it. This still results, and I'm kind of staying away from equations in this one because I'm trying to give you a higher level understanding. But this is a nonlinear equation. You have to do an iterative method to solve it. It's a not directly solvable method, so if you use Newton-Raphson. But this is effective for mostly DC characteristics in the forward region, which is where we usually want to operate these kind of, or stimulate and operate our photovoltaic cells. This usually makes sense. But we want to go a little bit more. So if we actually bring back those nonlinear parts, so bring back the parallel capacitance and series inductance. One thing I want to note is that this is you see the variableness of this capacitor. It does change with voltage, and I'll talk about that in a little bit. But we can't just say, oh, it's about 1 microfarad. You actually need to see how that changes with voltage because it's actually relatively significant, and I'll show some of that. And the thing that was left out in the other model was this reverse breakdown. And the way that we model that is using a voltage offset and then a diode in the opposite direction. And I'll show you this in the next slide, I believe. Wait, oh, gosh. Okay, so with that model in mind, so here's the forward characteristics that we got before. And this is the forward diode. So this is this diode engaging. But as we reverse bias this, so we put positive, flip the bias on this, eventually you actually get current going through this way. But it's not going to flow until this voltage is enough to compensate this offset voltage, this breakdown voltage. So in the picture, and I put these lines here because actually this tends to be about 10 volts, and this tends to be 1/2 volts. So this is kind of, you can extend this in your mind a little bit past the screen over there. So once you hit that breakdown voltage, it acts like a diode in the opposite direction. Okay? Oh, another thing I just wanted to note, so this angle here is the shunt resistance. So if you actually just look at the short circuit current and look just at that slope that you're getting there, that maps back to this shunt resistance. And when the diode is fully conducting, or so when you're in this region, the forward diode is fully conducting, and you mostly just see the series resistance. These are just ways where you want to look at on the curve to measure those things. Not as important for just understanding how it works. This is the general model. Okay, so now the capacitance. This is actually I guess my favorite part. I'm not sure why, but so there's 3 different types of capacitances, and the main 2 you're probably more familiar with is junction capacitance. So when you have a PN junction, remember you have the buildup of charges on the side and on each side of the junction. This is back to your diode model. And as you change the voltage across it, you'll get a change in the junction width, and then you'll have increasing capacitance as you increase the voltage across it. So really what I'm trying to say is here, this area, and this is a log scale, as you increase the voltage, you'll get a small increase in the capacitance that you get. But once we get to a certain point where going back to the IV curve, I like to think of this as the maximum power point. It's kind of hard to flip in your head, but so this here you're actually getting more current that's going through the diode. Oops, sorry. And so you're getting more current through the diode there, and that's what's giving you your diffusion capacitance. So you're getting more current going through that diode, and so that becomes a function of the current, the PV current. And then the last part, so this is from other data that has been, other papers that have looked at this, but no papers I've actually found have actually measured the last part, which is the avalanche capacitance. When you go much further, so this is not very far along in the cycle, when you go much further in the negative direction with the voltage, and you see that reverse breakdown, you'll actually see the capacitance start to go back up. So, and I'll show you in some actual data that I've taken, but we'll see that the capacitance will start to go back up. And that's never, I won't say never, I didn't find any literature on that, that's modeled that part. So I added that in this model. Okay. So now this is the full model, and sure we have, you like to put a bunch of model parameters on a page and say, of course this is how the PV should work, but can we actually extract parameters and have a good fitting with real data? So let's try. So designed a series of 3 different tests. This may seem a little involved, but once you do this full set of tests, you can completely parameterize the cell and simulate it. So the first one is relatively straightforward. You want to look at the IV curve, just looking at the DC part. And all you need for that is the DC source and the PV cell. And we actually use the Keithley, it's a source load. But these tests are actually all done in dark, so there's no light on them. But then the model, because using just mathematical relations, we can bring those back into a model with irradiance. So we can do it simulating with light hitting the panel as well. All right, the second one is just an AC sleep test, so we'll do some AC analysis as well. And then the third one is also AC analysis, but using the DC offset with that. And the first test goes through and looks for the, this would be shunt resistance, to find the shunt resistance and the 2 diode forward and reverse diode characteristics. You can extract all that from test 1. Test 2 focuses on the AC characteristics, so the series resistance and the inductance. And the last one, you can find the breakdown voltage and all the capacitance parameters. So if you really actually didn't care about these things, you could just do test 1, get the IV characteristics, model it, and be done. So this kind of just, each test is an added layer of complexity, which you may or may not want to incorporate. Okay. So let's start with test 1, the more straightforward one. So this is, we looked at 2 different cells, and these are 6x6 cells, so they're the common ones that you'll see on most PV panels. The first one is a polycrystalline cell. It's a slightly higher grade than the monocrystalline one. And if you notice the scales here, these are just going to 1/2 volt in the forward direction, but all the way to -12. So you can kind of see the breakdown region happening here, and then we're going into a reverse breakdown, also called avalanche. There's a few different mechanisms, but I just generalized it with breakdown or avalanche. And this one, you'll notice that it has the breakdown as well, but this is a much higher slope. It's also going to a larger negative voltage. I believe the higher negative voltage has to do with the crystalline structure, because it's mono versus poly, so it has better reverse characteristics. And then this angle has to do with the shunt resistance. The shunt resistance here is much higher than it is there, and I believe this one has to do with the lower grade. So this is a better crystalline structure, but a lower grade, lower quality of PV cell. Okay, so from this, we're able to extract all the necessary parameters to get the forward, this diode, and I'm not going into all the details here, unless you really want to get into how to model this. We can talk after. And then we also get the forward and reverse diode characteristics, and we can get the shunt resistance out of this. Oh, am I at time? Okay. So next, we want to look at these AC characteristics. So let's look at the shunt resistance, series and resistance and inductance. So how do we actually find these values? And note the inductance tend to be relatively small. You have really small leads, So you're not really going to have a very large inductance here, and it's only going to come through at higher frequencies. So what we do is we have to look at first the AC model. And some people hate AC models, but I didn't like them at first, but I've grown to appreciate them. So when we go to the small signal equivalent, we actually have to take all of, we can stick with the same model, but we take all of these things that depend on lots of factors. So they have to depend, you know, the amount of photocurrent depends on the amount of light hitting it. And these parameters all depend on where it's operating, the voltage and the current. So we take that and we kind of put it into a parallel resistance. And this is variable, and it will depend on what operating point we're at. But the things that we want to look at next are the series resistance, inductance, and then the parallel capacitance. So what we can do to find the series resistance and inductance is, here's the AC model. If we do the sweep of frequency, I'm going to direct you towards the outer part of the curve. So there's this point, remember, the resonance point? So that's the point where these two, the capacitance, inductance, and this RP is essentially 0. We are left only with the RS. Everything else cancels out except for the series resistance. So if we can measure this point approximately, we can get the series resistance pretty accurately. The second part is once we go above that, we see the inductance characteristics start to dominate. All right, because it's stopped acting as a capacitor. The capacitor is here, resistance point, and then inductance parameters start to take over. So using that knowledge, we can take a sweep at the higher frequency of our cell using the AC test and just try to find those specific parameters. So you do this with, I did it for both. I'm only showing the polycrystalline cell here. They're actually they're very similar. And although this isn't perfect, so this is in the higher frequency, so this is just this part of the curve, following me. So we make sure that we're going to relative resonance, and these points we're in the decimal area in terms of impedance, so this will give you an approximate value for that. And then once you look at this area, you can actually, knowing the frequency and some of the other parameters, you can calculate out the inductance. And so doing that, now we've figured out those two parameters. So the last one that we have is the capacitance, which is actually this took a long time to really get. But luckily it comes out pretty nicely. So you have to calculate this out, but I'm just going to show you the results. So once you do all the right calculations, you can get the capacitance out over as you vary the voltage. And so we see that this area is the junction capacitance. This is the diffusion capacitance area. And you can kind of see it here. If we had gone a little bit farther and without overheating the element, that's one of the difficulties, we would actually see it start to go up a little bit more here. So that's the avalanche capacitance that a lot of people don't incorporate. And so this is done mostly through model fitting. And I'm leaving out all the parameters because it's kind of tedious. But you can, of course, read the paper if you want. And then the same thing is done for the monocell. Notice here we actually don't see the avalanche capacitance become dominant. I believe it's just we didn't go further enough into the reverse bias region, mostly due to thermal limitations. The further you go this way, the hotter the cell gets, and we don't have a very good heat sunk environment, so we're not able to really maintain a perfect temperature. So that's a limitation of our lab. But with this, we have the full nonlinear capacitance over the full voltage range. So with all of these parameters now, we've identified through these three tests. And the current through the photocurrent is actually a function of temperature and the amount of irradiance hitting the panel. So that's our mostly user set and found through an equation. What we've done is done that entire model, which luckily fits very nicely into this little tiny Simulink block. If you open the Simulink block, it actually takes up the entire screen. I'll spare you that. But in this way, this is now doing all of that. We can, trust me, you can parameterize a cell And then you can put all the parameters, put it into this little box, and then now you can just simulate that cell. So, and actually don't have the capacitance showing through here, but you can also get an independent block for just the capacitance measurement if you want. So we've implemented it this way, and then started to do a series of string cells, and that's done some preliminary results. They're not included here, but using this tool you can do a very large set of strings all in MATLAB relatively quickly. So that's all I was going to go up to today. But just to recap, we looked at a fully modeled, so including reverse characteristics and dynamic characteristics, and with a nonlinear capacitance in particular. And we looked at a 3-part parameter identification techniques that use both AC and DC and AC tests, and just common MIME equipment. This doesn't need a solar simulator. You need an AC frequency generator, a DC source, and I use a tectonic scope or some sort of AC analysis tool. And then everything is implemented in Simulink, and it actually, I can almost got to the point where I could just give you the block and you don't have to know anything about the model and it would just work. So I guess if you're interested in talking to me about that, you can. Of course, all the people who help with all the research, and thank you. Are there any questions?
Yeah, so I was wondering on slide 1116. You said that. Yeah. So on slide 11, you said that your RS value is really small, so it's pretty difficult to measure. And RS and LS are coming from their leads. So I was wondering how sensitive is output of your PV string or your whole module on those RS and LS values, because any distance in a cable to measure the cell would affect those values.
Yes. So the way that, because we're doing, let's see.
It's like a little bit of a small change in RS. Does that have a large effect, or is it a pretty small effect in your total modeling of your cell?
If I understand the question correctly, so is this value itself, the RS value, will mostly, is this the right? Let me see if it's the right one. Affects this angle right here. So if you have a large RS, it will kind of slope out this way.
Okay.
So that's incorrect, and it depends on how accurate you want it to be to your data sheet, or there's a few different ways that you can adjust these values. But they tend to be, they're relatively small, and they do affect this area. So
but it hasn't been a big problem.
Yeah, generally we actually get pretty good fitting, but if it's very much wrong, you would get a divergence there.
Okay.
Yeah. It depends also what type of test you're doing. If you're doing like convergent tests, this value doesn't matter, but if you're doing exact modeling. Any other questions, guys? Oh, actually, that's a really good question. On the AC part?
Yeah.
So I put it in here just for completeness. Everything that I've done is actually use just the magnitude, and actually all of the calculations that I do looks just at the magnitude. Mostly because I think the magnitude is easier to calculate. The way that we do it, we actually we put a scope, an AC signal on the voltage waveform and the current waveform, and we look at the amplitude of that, and that's just a lot easier to do signal processing on. I looked at trying to do the phase difference, but the problem is the phase is not, this doesn't go all the way to 90. This is from negative 90 to positive 90. It's not labeled well. But depending on how close these parameters are, it won't necessarily, if you change this and move it in a little bit, you won't get all the way to 90. So I think the phase, when it flips over, it tells you if it's in the inductive region or if it's in the capacitive region over here. So yeah, there may be merit to looking into that, but I focus mainly on the magnitude. So it's kind of an open question.
Assuming that you make a transfer function of this model for the voltage output to the radiant input, is this model, does it have any unstable features in the body of with the gain margin and the phase margin? Do they tend to go negative at any frequency regions of operation?
For, you mean just like on its own?
Yes, E of S, because the model, I just wanted to understand if the model predicts any instability like TV as a system, like the voltage output and the radiant input, and this becomes a transfer function E of S over radiant of S. And then this transfer, when you do a voltage part of that, you find any unstable results of operating gate cannot operate your system.
I haven't done that analysis exactly, but I think, yeah, once you attach something to it, we're actually going to be doing that part like a little bit more. We're adding on a DC-DC converter and then seeing the whole system itself. One thing that really good point you bring up is the irradiance change. A lot of people kind of just assume it's constant, but it does change, and it can, especially here where it's cloudy and windy, the irradiance can go up and down. And I think, Raj, you've looked at some of that data too. It can change very quickly. And so we haven't, I don't think, in general, done enough analysis on quick transients and how much that can affect the stability loop or other things like that. Yeah, I haven't done that yet. That's a... It's possible, yeah. I haven't really looked at it as much, but... Any other questions? Okay. Hi, thank you.
Okay, thanks, Catherine. Our second speaker today is Yue Cao, and he obtained undergraduate degrees in ECE and mathematics from the University of Tennessee, and is currently a master's student at UIUC here, where he is a James N. Henderson Fellow and the Pels Chair. He's currently working under Professor Philip Krein on power electronics and motor drives.
What is this? Huh? Maybe not. Well, I don't know. Thank you, everyone. This presentation is primarily based on an industry project beginning in 2011, and it's been going through just recently, and pretty much everything's done, and it's been very interesting, very unique topic that is pretty different from other research that's been done in this group. And part of this presentation is also from the qualified exam, so will be my recognized. Yes, and but it's more than that. That's about half. It's about a background and motivation, and over that, beyond that, it's more simulation results, experiment results, and also some discussion and limitation, future work. Okay, the title is the Average Modeling Approach of Hybrid Power Systems for Mobile Refrigeration Applications. It has three parts: mobile refrigeration application, hybrid system, and average modeling. So those are the outlines I'm going to talk about for this presentation. So mobile refrigeration unit is a thing like this on a truck. I assume nobody really looks at this truck like this, but if you look closely, you should notice something like this. And it's just like on the right street, you'll see a couple of those. And it consists of a power system and a thermal system. The conventional power system is just a diesel engine, and thermal system is a compressor, condenser, evaporator, things like that. And how it works is the diesel engine powers the compressor, and the compressor do condensing and evaporating work here for the thermal part. The problem with this is the pollution. That's the predominant issue, because when the truck is idling, the truck needs to upload and load and upload products, but it still needs to run constantly. So there's a pollution issue with that. And the government has several rules already set for this to reduce or even eliminate things like that. So start from 2011, the company called Thermo King and the UFI and also Mechanical Engineer Department collaborate on this project. The proposed idea is to eliminate the diesel engine and just replace with AC machine and the variable frequency drive system. So part of the power source coming from the main engine, and the other power source is the lithium-ion battery. This system, we might think the hybrid system is more efficient, but not necessarily, because in the hybrid electric vehicle, it's obviously efficient because of the regenerative braking. Okay, but for this system, it does not have that feature, so it's not necessarily efficient. So we want to have a study on efficiency and the cost of the system, like how many years can we break even. So we are interested in a hybrid parallel system like this. Our goal is to analyze long-term efficiency and cost effectiveness. So we need a fast, accurate, and robust model to do this work. So we are not interested in like within seconds of what the machine transient waveforms look like. We are not interested in that. We are interested in overall efficiency and the power levels. So we have a couple of challenges. The challenges, the first challenge is at the AC generator side. That's directly coupled with the truck engine. The truck engine has a dynamic drive cycle that has a very wide range of operating speed, and it can stop, it can run, it's very complicated. An induction motor is tied with the compressor. Compressor is the model from the thermal system, so we need a certain interface between this electric model and thermal model. Another challenge is how I make everything work together here as a system. So we define some of the specifications at the beginning, that induction motor is about 10 kilowatt range, and AC generator is about 18 kilowatt range, and DC link is a 700 volt, battery pack is the 300 to 400 volt. Everything else is just a power conversion. The idea is to model this based on equivalent steady state approaches for loss models. So I model this as the loss unit. For example, I can calculate the output power required and then do circuit analysis on a steady state approach and find out the input power. So the difference is the power loss. And some similar approaches for other units that I'll cover a little later. So I will go back to photo. So I'll go back this way because I know this power, then I know this power, and I know this power, and so on. So the
in doing this,
you
obviously you're an electrical engineer.
Right.
You got rid of the testing mechanical system.
Right.
Okay. But don't the mechanical systems have a big impact in this?
Are you talking about mechanical losses?
Well, I'm talking about, you start with the AC generator, but really you've got a diesel engine.
Yes.
And then you end with the induction motor that's driving a compressor.
Right.
And you've got rid of that stuff. But doesn't that have a big impact?
Yes, we do. Yes, we do. I will talk about that later. There's mechanical losses also we model here between the engine generator. Based on the speed, there's mechanical losses, same as induction machine. Treat them, mechanical losses based on speed. Yeah. Everything is steady state, so we are interested in this steady state induction machine circuit. Just do power analysis, pretty simple. And it's controlled by volts per hertz controls, or scalar control. Like this is the control unit. It's not that complicated either, because we're not really too care about the precise control, and also other precise controls slow down the speed. And we take reference speed and desired torque from the thermal system and put into this output power and do all the current voltage analysis and find the input power. The power electronics units are modeled as device losses. That's primarily loss come from. In semiconductor devices like IGBT and diode, there is switching loss and conduction losses. Switching loss is like this. I don't have to talk too much. You guys have taken that course. And the conduction loss can be modeled as this. The formula is this to calculate those losses based on the frequency and the bus voltage and the current that we get out of from the model after it. And the permanent magnetic synchronous machine is used for the generator. Again, it is an equivalent steady-state model. And address Professor Orby's concern here. This column is the mechanical losses, and it's modeled perfectly as a quadratic function based on speed. And we use so the speed here is tied to the truck engine, and truck engine is tied to a drive profile. So this, so we know that RPM, we can find all the voltage and the frequency and so on, and eventually do the circuit analysis. And the mechanical loss is also predicted here. And drive cycle is something we do not have at the beginning, but we propose something from published test data. And it's something like this. We did a little modification to model from a 10-hour day from 0 seconds to 36,000 seconds, which is 10 hours exactly. And what happens here is the truck is running in this region, but it stops in this region. During the stop, there can be other events like door opening and closing, truck products loading, uploading, so things can get very complicated. Yeah.
What's confusing about that graph is you say that's time in seconds.
Right.
Look at 0, 0.5, 1, 1.52.
Oh, yeah?
Look over on,
yeah.
I don't know how many people here picked up on that or not.
Right.
But that's a little confusing because you see that
time
in seconds and you think you're talking about seconds. And so it's better if you use like hours.
Full scale. For hours. Okay.
I mean, it just gets confusing.
Okay.
To the casual viewer.
Right. Okay, understand. That's a very good point. But I mean, in simulation, it's actually have to use second to do the simulation work. Yeah, but that's a very good point. The lithium-ion battery is a little improved from previous model. It's modeled like this: internal resistance and some of the second-minute hour RC models, and this comes from the capacitive effect inside the lithium-ion battery. And these RCs and can be tested. Can be tested, and we can test it based on the function of SOC, and we can interpolate it or curve fitting through these testing points. The previous paper fit these points based on this curve, but the problem with that, they have a negative curve here, so it creates the instability of the system. So I improved that based on this curve fitting method, and that looks very good. And so on, yeah. So some of the interesting stuff here, simulation results. So we run this system, we integrate this power system with the thermal system and run from 1 p.m. to 3:30 p.m., which is, again, it's on the second scale, it's like 20,000 seconds to 29,000 seconds. And we propose the ambient temperature is this, and the required inside temperature is like this. And here is some of the events happening: door opens and closes, and a motor operating and not operating, and battery charging and discharging. So we also have all the power levels at each subsystem. This is the generator, rectifier, converter. This is the inverter, motor, so on. This is battery powers and battery state of charge, and the battery terminal voltage. And these two are the efficiency curves we get. So the first one is engine power supply efficiency. That's defined as the power out into the compressor divided by the power required into the generator, excluding the power that is used to charge a battery. And this one is the battery supply efficiency. I did a little detailed model in simulating power systems that includes all the subsystems previously, but that one can simulate very, very slowly on the second basis. So I cannot model throughout these many seconds, but I pick some points based on the the loading requirement we have and plot against each other, and looks like it's quite close. The efficiency is quite close. The detail model is a little less efficient because of the harmonics and also other factors that's more refined. The experiment is pretty hard to work out because it is a huge system. Simulation for detailed? Detailed, they use 2 microseconds. And the average...
Going to be 2 microseconds.
Uh-huh.
Micro.
Yeah.
Why did you use 2 microseconds for your simulation time?
What do you mean for?
I see. I see times as hours here.
Right. Yes, still hours. Yeah.
I mean, you're like minute stuff, and then you say I'm using 2 microseconds. Why 2 microseconds?
2 microseconds for time steps. Yeah.
What fast dynamics are you capturing that requires 2 microseconds? Because when you presented your model, you said, I'm using a steady state model for my inductor here. You showed us a battery model that has seconds and minutes and hours. And see, when we do transient stability simulation, for those of you who've taken 576, you know, Solar starts out with very detailed models, and then you say, well, we can ignore the stator transients because they're fast. But in a 2 microsecond time scale, stator transients are still there. Okay, did you include stator transients in your generator model?
Yes, yes.
The stator transients in your generator model? I mean, what type of generator? I don't know why you're using fast dynamics.
Like there are like the fast dynamics. One thing I can think of is in the power electronics, the semiconductor devices. There are snubber circuits, and also and the switching frequency at 10 kilohertz. So things like that can slow down the system. And for the machine-wise, I'm not too sure actually what slows down that much.
In your earlier presentation, where I was confused,
right?
You are ignoring certain things. Like there's a lot of dynamics associated with the diesel engine. There's a lot of dynamics associated with the compressor on the refrigeration side, with stator transients, blah blah blah. If you had said, you know what, I'm ignoring all those fast dynamics, I'd be fine. But then you tell me the time step is 2 microseconds.
Right.
I know you're detailed power electronics. I understand your power electronics guys, so power electronics dual.
Right.
Right. But it doesn't match the rest, so then your simulations take forever, and that's the confusing part to me.
That
is why did you need to handle the power electronics at 2 microseconds, but you just said to the compressor, you're just like a constant load. Instead of the diesel engine, which our friends on the mechanical engineering side would say, you're missing the main part of the simulation.
So,
or if you were here, he'd say, you're missing the machine simulation. But I agree, the stator transients for what you're doing on hours can be ignored.
Right. I mean, it is ignored for the average model. Detail. It's just for validation purpose. It's just for validation. I mean, I don't like even in detail. I don't care about those transient or those stuff. I just measure the output power and input power and divide it. That's what I did. All I did in the detailed model. That's all. I didn't really look at all those.
You got rid of all those power electronic transients.
Yeah. Yeah, but I'm not too sure about the machine part. Yeah. Okay. Experiment. It's pretty huge experiment system. So we break down to 3 parts. The first part is active front-end test. It's from the generator, rectifier, and converter. And this is conducted by Thermo King on a full scale. So these are the experiment results from them, actually. So they're showing the solid line is the measured data, and the dashed line is the simulated data. So it looks pretty close to each other, and also efficiency is within 2% accuracy. And this one is the rectifier efficiency, and the model also tells me in the upper 90s. So, what's that?
Is that generator speed?
That's generator speed. Yeah, yeah. It's from 1,000 to 5,000-ish. Yeah. And the second part is the battery experiments. Battery, it's already tested by a previous student here a couple of years ago. And what I did is to plot my simulation results compared to his experiment data, and it's more accurate compared to his previous. These two are the just second RC time constant. This one is the overall terminal voltage, so this one may be more meaningful to you guys. The last part is conducted at UIUC, and here is the proposed modular inverter and dyno motor for this test. And inside the modular inverter, there's a power stage and communication stage or control stage. What I propose to do, I haven't really finished this yet. Propose to do is to model to test out the curves like this and plot against the simulation results and see the differences. With that, so our goal is to eventually see if it's really better to convert to hybrid or plug-in options. So we did some preliminary analysis. We have this kind of assumptions, and each topology gives me different energy cost. The graph here shows for the first 8 years, the conventional system starts with the minimum cost at the beginning, but in the end, it had the highest cost. But others has a higher initial cost, like the battery pack and also chargers and other stuff, power electronics. But with the time going on, after 3 years, the plug-in option already beat the system. After 4 years, the hybrid system is also better than the conventional. Yeah, this is just preliminary. So, but the trend is kind of meaningful. Limitations here. The model runs fast by trading off fidelity. So this one is not intended for hardware design, but is mostly for system study, efficiency study. And in the simulation study, we only simulated on a hot summer day and cold temperature inside, but things can be reversed, like on a cold day, I want warm air inside, so things can be different. And also, the truck can run not like that drive cycle, but just run on a highway without any stops, so the results may be something different too. And we use only hybrid topologies here, parallel hybrid topologies here, so there may be some other topologies that work better. Some future work, possible future work, maybe advanced motor drive control techniques for higher efficiency. And I think this is pretty interesting with some great interfacing problems like government policy, smart grid pricing, system stability, because this is just like plug-in hybrid vehicle. This is plug-in hybrid mobile refrigeration unit, so that can have some impact on the grid in the long run. So that might be some study we're interested. That's all. Thank you. Yes.
So the battery charging, I think you have some graph where it
yes.
charges so often.
Which one? This one? No, wait. This one? Yes, yeah.
Yeah, so the question is that battery charging, which battery is that? Is it charging from the grid, or where is it?
Charging from the diesel engine, the truck diesel engine.
Okay. And is the diesel engine always on? Why is it charging in like vehicles instead of?
These parts is the charging. The orange is charging, right? Mm-hmm. This part is when the truck is running.
Okay.
Yeah.
So you're charging it from the diesel engine, but the diesel engine is always also on. Is that?
Diesel engine is not always
It's not always on. Only
yeah.
when it's starting up and moving.
Right.
And then how does it know when to charge it? Is it detect the state of charge?
Right. It has a preset like limit below like 0.95 state of charge, or the system commands it to charge. Yeah.
Yeah, I had a similar question, but it was with the actual diesel engine, and
Where?
I'm not sure if it was you or maybe someone else on the other like mechanical side. Did you look into like a variable transmission or a certain idle speed based upon like the efficiency of the engine versus the efficiency of your connected generator?
No, we haven't. Okay. We assume it's a single gear transmission. Okay. Yeah.
Because that's one thing that can have some very big efficiency effects, because the diesel engine has one primary like high efficiency point, and then the generator as well. The permanent generator is not highly efficient overall operating speeds.
Mm-hmm.
That would be some good future work.
Yeah, that's a very good point. Yeah, I might talk more of that to the mechanical people. Yeah. Okay. Any other questions?
What size is your battery?
The battery pack is 6 kilowatts, 1 kilowatt hour, and 350 volts. Yeah.
Do you consider the degradation of the batteries? Like,
what's that?
The degradation of the batteries.
Yes, a very good point.
You're
right.
Like 8 years.
Right.
Over 8 years, the batteries these days.
Yes. In the cost here, it includes. It does not include that factor. We assume we do not change the battery over 8 years. But I think battery technology these days can last up to 10 years. But I think that's not very, yeah. Right. No, I haven't do that part. But it does include, for the conventional, it does include like oil change, things like that for the diesel part. So, yeah. Yes.
I just want to ask, the battery you used is lithium, right?
Lithium-ion battery. Lithium
battery, right? But maybe most of battery in the trucks are lead acid.
Lead acid.
Right.
Yeah, that's the old technology. Yeah.
So why you don't use that?
Lithium-ion, right? Good question. Lithium-ion battery has a lot higher energy density, right, and also it's environmental friendly. So if you look at some of the recent electric vehicles like Nissan Leaf and Tesla motor, those all use lithium-ion batteries instead of lead acid.
So your scenario is for a hybrid vehicle, right?
Yes. Hybrid electric for the mobile refrigeration.
Right.
It does not power the truck. Yeah.
Yeah.
It's for that compressor, the thermal system.
So this is an extra battery only for.
Right. Extra battery just for the mobile system, not the refrigeration system. Not for the. Has nothing to do with the truck.
Oh, okay.
Yeah.
Okay.
What makes you think that the lead acid battery is worse for the environment? It's like 99% recyclable. It's like the most recycled product on Earth. It's lead acid battery.
Okay. It's lead. Yeah, I guess I don't know, maybe the manufacturing process involves some pollution, but
I guess I'm trying to say I think you're wrong.
I don't know the exact details, but what I read in literature is they promote these kind of features for lithium-ion.
Well, certainly the lithium-ion battery guys will promote it.
Yeah.
Sure. But I think you don't want to give lead-acid batteries a bad rep, because they are perhaps the most recycled product on Earth. So they are quite environmentally friendly, as it turns out.
Okay. Okay. Thank you.
I'm not sure if you mentioned this. How does the weight of the mechanical one?
Weight?
Yeah, for like a
Right. Yeah, it's not that heavier compared to the other parts of the truck. It's a truck, so.
Well, when you're adding, it weighs 200 more pounds than the system you're replacing, like a pallet.
Yeah, it's yeah, I agree. Yeah, a little heavier, but compared to the products, a few tons of products that the truck might carry, so that's only a fraction of it. That's not considered actually. So, but maybe in the future we need to do a small factor, 1.05 factor or something like that. So, yeah. Yeah, this is really new work, so a lot of improvement, I think, inside.
So what would you use
Induction machine, yeah, because of the, is it time? Induction machine, it's because it does not require external field excitation compared to synchronous machine, and also the variable speed is, I think it's easier for the synchronous machine because of the dynamic response from the thermal system. So. Right. Yeah, actually Professor Klein asked me to model PMSM for induction machine also. I haven't done that, so that's also another study to see which one. But PMSM is more cost, right? Yeah, so. Yeah, sure, but the industry people, the initial cost is also important. Yeah, yeah.
Usually in electric machines, the initial cost is nothing. It's the operational cost, that's everything.
Really?
Yeah.
Okay. Okay.